So here's question 3, the first circuit problem, and I'm going to solve this circuit. So the first step, and this guides you through it, is to add all these capacitors to get a single equivalent capacitor. So if you know how to do that, or think you know how to do it, just pause the video and do it before you watch what I do. If not, I'll walk you through this one. So the first step is, this is in series with something that's not simple. So you have to simplify this to a single capacitor. And since these two are simply in parallel, you just add them. So add those two and see what you get and come back. So you added the 16.1 to the 23.9, and it comes out to exactly 40. So a single capacitor of 40 is exactly equivalent to those two in parallel. Now we got to add these in series. So we have a 35.9 and a 40, and so it's going to be, I know from experience that it's going to be smaller than the smallest one. And if they were both 40s and they were in series, you would get a 20. So I can guess that this is going to end up being something like a 19 microfarads. So add those two in series and see what you get. Okay, so you know when you're adding in series, you add reciprocals. So 1 over 35.9 plus 1 over 40, which is those two together. And that's 1 over the answer, so you have to invert that again. So that's why I write it this way. So if you take 1 over and then invert it, you get 18.92. Make sure you can do that math. And that's what I said, it would be around 19. So the total of all three of those, if you put a single capacitor of 18.92 and replace these three, it's going to be the same thing. So, but that's the sum of these. What we really want to find out is how much charge is on each one and what's the voltage across each one. So we have to start with this one and work our way backwards. So find out how much charge the battery would put on a single capacitor of this amount. So we're calling this C total or C123, and the charge on this one is going to be what we call Q total. So just use your equation and calculate that. Okay, to get the charge, we use this equation that relates charge, capacitance, and voltage, and we solve for charge. So the total charge is going to be the total capacitance times the total voltage. So we multiply those together and we get 238.39. And the answer is going to be 238, but we save those extra digits for calculation purposes. The last question, there's a misprint which I corrected. What is the total equivalent energy delivered by the battery stored on the three capacitors? So that's U total. So on your equation sheet, you'll find the equations for energy. U C for capacitor, and it's 1/2 Q times V. Now, since we have this relationship, this can also be written two other ways, which is sometimes useful: 1/2 CV squared or 1/2 Q squared over C. Those are just derived by using this equation. So since we have the Q and the V, we'll use this equation, 1/2 QV, and that gives us the result. That's the answer with extra digits, so you report 1500, and that would be nanojoules. Yeah, I need to fix that. That needs editing. Now we have to step our way back and find of this charge how much is on each capacitor, and of the total voltage, how much voltage is across. Remember, we're always measuring voltage by putting the probes on each side. We're measuring the voltage across. And so if there's 12.6 volts across all three, there has to be less voltage across C3, and capacitors in parallel are in parallel, so that means they have the same voltage. So what you should know is that the voltage here plus the voltage here has to equal 12.6. And the charge is even a little more complicated. Since the battery is sending out 238 nanocoulombs of charge, it all has to go here, and it all has to come back from there. So this is what you have to know, is that we do know, because this is in series with the battery, that it has to have 238 nanocoulombs of charge. And what we know is that there has to be 238 nanocoulombs of charge split between these two, because they were in parallel, right? Because if we remove 238 charges from here, some from here, some from here, so that's what we have to figure out. So since we know that all of the charge leaving the battery has to go here, we can write down that on C3, the charge is 238. And once we know the charge and we know the capacitance, we can find the voltage just using, C equals Q over V. So V is going to be Q over C. But be careful, we're going to get V1, the voltage across this capacitor, is going to be Q1 divided by C1. So do that and see what you get. So Q1 is that, for reasons I explained, not so obvious. C1 is pretty easy. That should be C3, excuse me. I screwed up. This is all C3. So we're finding the voltage across 3, the charge on 3, and the capacitance of 3. And what I said was the charge on 3, is the full charge from the battery. So that's that. And the capacitance of 3 is 35.9, and that gives us, and this is microcoulombs, and nanocoulombs and nanofarads, so we get volts. So now we know that the voltage across this capacitor is 6.64 volts. And that makes sense because the battery is 12 volts. So about half of it is there. The other half is going to be across these two because they're in parallel. So if we simply subtract this from the 12.6, right, the remaining voltage has to be on the other one. So let's do that subtraction. Okay, so I did the calculation, 16.1 times 5.96, the voltage across 1, and that gave me 95.95 nanocoulombs. And then C2, 23.9 times the same voltage, because they're in parallel, gave me 142.4 nanocoulombs. And notice I can check whether I'm right or not. If I add these two together, right, the total charge there has to be equal to the charge here. And that's what I'll get. I'll get pretty close to the, except for rounding, the 238.39. And so now I know that I can be certain that all these values are correct. And so I just leave it to you to calculate U for each one of those, simply using that U1 is going to be 1/2 Q1 V1, and so on for 2 and 3. And those three numbers, the number you get here, here, and here, added together, should add to that, if you don't make any mistakes. Okay, that completes this circuit. Okay, question 4, you know the routine. So we have a little bit different circuit. So look at this and see if you can find the total equivalent capacitance. Make an attempt, think about it, and then see what I do. Don't just wait for me to do it. Try. Okay, push yourself to understand, to really understand how this all works. So we have 2 in series. That's always less capacitance because there's more space between the 2 plates that are being charged. So I added the C2 and the C3 as 1 over C1 plus 1 over C2. I'll write that out. So 1 over 27.5 plus 1 over 33.3. But that's 1 over the answer, so you have to invert that. And check yourself. If you're adding 2 30s, this is averaging about 30. If you were adding 2 30s in series, you would get about half the capacitance. Try to understand that. Then you know what to expect. So I'm expecting 15. You see what I got? 15.06. So that was a pretty good guess. So I take those two numbers, add them, and then invert them again, and I get 15.6 nanofarads. Now, that 15.6 is equivalent to these two in series. It's going to behave the same way in the circuit. And resistors in parallel simply add. So if I add the 15.06 to the 13.3, I get the total. And in this box, you're going to write 28.4 because you only want 3 digits, but we got to save this number for calculation purposes. Okay, now we have the total. Now we want to find what is the charge on this capacitor that it doesn't exist. It's just a mathematical equivalence of these 3. But we're going to find Q total and the amount of energy that the battery stores in that one capacitor. And so do that and come back. Okay, if I'm showing my work, I write the equation, I solve it for Q, and then I will put the numbers in, the C total. Notice you have subscripts, because you'll see later, you can't mix C total for Q1. You want to make sure that everything in this equation is either a 1, a 2, a 3, or a total, or something that's the same. And I'll show you how that can mess you up later. So the Q total is going to be the C total, keep the extra digits, with the V total, which is given, and no, that's the C total. We get this. So C total times V gives us this. Then once we have the Q, the energy equation is 1/2 QV. So we take this Q and we multiply it by V and then take a half. And you should get this number, 2251. So that would be 2250. It's in nanojoules. I should have put it in microjoules. So if we move from nano to micro, we move the decimal point 3 places. So it just looks better as microjoules rather than 2,251 nanojoules. It would be better to write it this way, but since this is given, you just put it in those units. Okay, so now we know how much energy and charge is on that single equivalent capacitor of these three, but now we have to go back and get, okay, how much charge is on each one, and what's the voltage across? And this is an important concept. The charge is on the capacitor. The voltage is always across, right? When we measure a voltage, we put the voltmeter on both sides of the capacitor. So it's kind of like the energy difference between, or the voltage difference between one side and the other. So we always use the word across. It's never on or in, it's always across. That's an important concept. So, how do we understand this? So the charge, this amount of charges leaves the battery and goes over here, and that amount of charges comes from here back to the battery. So the battery just sends 357 nanocoulombs of charge from one side to the other. So in this case, this total charge is not on any one capacitor, because you see it splits. This is important. It splits at a junction. So now the charge on here, if you understand this, and this is an important and not easy idea, is whatever charge goes here has to leave there. So even if these are different in size, because they're in series, they always have the same charge. So the charge on here will equal the charge on there, and whatever this charge is, plus what charge goes there, has to equal the total charge, right? Whatever goes to this side, if there's 10 units of charge and 4 goes here, then 6 have to go there. That's the 10 units that left the battery. So push yourself to understand how this circuit works, and you won't have to memorize a half a dozen rules and not really understand what you're doing. Okay, now what we know is that the voltage, so how do we start this? We know the voltage between here and here across all the capacitors is 12.6 volts. So that means there's 12.6 volts here. So knowing the capacitance and the voltage, we can find the amount of charge there. So in this case, we're not going to find Q total, we're going to find Q1. We have to use C1 and V1. But in this circuit, follow this, the V1 is the full battery voltage because of the circuit, because this one capacitor has a direct path back to the battery. I hope that makes sense. Then, once we know the charge here, whatever remains of the total has to be here. And if we remember and understand that these two have to have the same charge, then whatever that charge is, it's on both of them. then we can use the charge to find out what the voltage is. So between here and here is 12.6 volts. So part of it is going to be here and part of it is going to be there. So whatever the voltage across C2 is, the voltage across C3, it has to add to 12.6. Okay, see how far you can get with that, and then come back and watch me do it. Try your best to finish it on your own. Okay, so I used the equation Q1. I'm finding Q1. I have to use C1. I have to use V1. It just so happens, it's not automatic, you got to be careful, that V1 is the total voltage. So I got that. And so let's put this in the table. We're doing C1, and what we saw was that C1 has a voltage of 12.6 because of the circuit, and now we found that Q1 is 16758, so I would put in 1.168 here. And then what I did was I took the 16758 and I subtracted it from the total, and I got that number. So that means that the charge, did I screw up? Oh, the charge on 2 and 3, remembering that it has to be the same, is going to be 190. They have the same charge, and you don't add that charge because they're in series. So if you add the 190 and the 168, or you add, these two numbers, you get the full charge back. Now the voltage, now that we have the charge on these two, and we know their capacitance, we can find the voltage. And then once we have the voltage, it's easy enough, right? It's easy to find the energy once you have those, because the energy is just going to be 1/2 QV. So that's just a calculation, and you can get the voltages. So let's finish all those calculations and then come back. Okay, there it is. We're going to get V2. So if we want V, it's going to be Q over C, but we're getting V2, so we got to use Q2 and C2. So Q2, the charge on 2, notice I used the unrounded number, and I divided by C2, and I get 690. Then if I take V3, and I take Q3, Q3 is the same, right? So Q2 and Q3 are the same. So I take the 189.78, and this time I divide it by the 33.3. Then I'm getting V3 because I'm taking Q3 and dividing it by C3, and I would get this number. And so those two numbers add to 12.9. 12.6, right? And that's what they should. So I could have taken this and subtracted from 12.6 and gotten that value, but by doing it this way, the V3, Q3 over C3, I kind of affirm that yes, that is the correct answer. I got it two different ways, and because those two numbers add to 12.6, I'm very confident that we have all the right answers. And you can finish it up by simply doing this. I'm going to leave that up to you. And that finishes questions 3 and 4 in assignment 6.